And in particular, I'll provide evidence that simplicity bias is, so there is a, look, so it's not, so yeah, so the outline of the talk is that I'll first introduce the distribution shift problem, and then I'll provide evidence that simplicity bias is one of the main reasons for the brittleness of neural networks to distribution shift. And I'll further present like more refinements of how simplicity bias can be detected and how to address them using a couple of algorithmic ideas. And then I'll present some evaluation results, and then we'll conclude the talk with some future directions as well. Okay. Okay, so there's a bit of lag between when I change the slide and when it appears on online. But let me begin. So distribution shift between training and test data is an important problem. So the pictures are still appearing. So the pictures will appear, but the point is, so I'll present pictures on two data sets. So one is Chameleon 17 and the other one is FMOW. So both of these are part of the wild benchmark. And in the left image, the task is that we are given a microscope image of a particular tissue, and then we want to classify whether it's a normal cell or a tumorous cell, right? So the class is whether it's a normal or tumor cell, and tumor cell, and then each column is coming from a different hospital, right? And during training, we get data from some hospitals, and during test time, whatever model we develop, we want it to be applicable not only on these particular hospitals, but also to any other hospital where we can deploy this, right? And there will indeed be few differences between the hospitals that we use at train time and test time. The demographics of the people who come to the hospitals that we got training data from, that could be somewhat different from the demographics of people who might be going to the hospital, which we are doing at test time. And similarly, like the microscope, the image which is used to do the microscope might also be different. So there are certainly some amount of differences between whatever we see during training data and then what we see during test time. Similarly, on the right-hand side, we have this other image, which is FMOW. So where the task is that we are taking a satellite image of a particular region, and we want to classify whether this contains like a shopping mall or a road or agricultural land and so on. And even here, the training data often comes from the past. So here, say 2000 to early 2010, and then the test data would be somewhat later because we train a model and then we want to be able to use it for a long enough period of time into the future. So the test data comes from late 2010, right? So here again, like there could be differences in terms of both the kind of buildings that people were constructing in 2000 versus maybe 2010. And similarly, the camera or the imaging instrument that was used between like the in the training data versus test data. So hopefully I have convinced you that being robust to these distribution shifts where there is there are some systematic differences between the training data and the test data is a important problem that needs addressing. And it turns out that if we don't do anything specifically to tackle this issue, it turns out that there is a loss of accuracy for various models because of distribution shift. In particular, so there are cases where the models can change from being highly accurate to somewhat close to random predictions. The picture is yet to come. So I can quickly explain what the picture would say. Basically, if you plot the in-domain accuracy on the x-axis and out-of-domain accuracy on the y-axis, it turns out that even when the in-domain, so ideally we would expect that whatever accuracy we are getting on the train domain is very similar to the accuracy that we are getting during in the test domain, right? But it turns out that there is a substantial gap between the accuracies that we see on the training domain and the accuracies that we see during the test domain. And this is the reason that even if the model is highly accurate on the training domain, it turns out it could be not so accurate in the test domain. And this talk is going to be primarily about why neural networks are robust to, why neural networks are brittle to distribution shift, and can we design new algorithms which enable these models to be more robust to distribution shift. Actually, I don't see any of the pictures coming up. maybe we can just do a PDF. If possible. I have emailed the slides. So, yeah, yeah, I have emailed the slides. Sorry about that. Okay, so I want you to look at the figure on the right here. So on the x-axis we have in distribution accuracy, and the y-axis we have out of distribution accuracy. If both of them were the same, then they should lie on the dotted black dotted line, which is basically x equal to y, right? So if whatever accuracy we were getting on the train distribution, if that can translate to test distribution, then the accuracy would lie on the black line. But it turns out that the accuracies, the blue dots, which are the actual accuracies of various different train models, they always lie below the black line, which means that the out of domain accuracy is like lower than the in domain accuracy. And we can see that in some of the cases, for example, to the extreme right, we see that for an in domain accuracy of 65, the out of domain accuracy is like less than 40%. So there is a substantial drop in out of distribution performance compared to the in distribution performance. And the question we are trying to understand is why neural networks are so brittle, and how do we make them more robust using some algorithmic insights. Okay, so let's start with a thought experiment. So if we are given the task of classifying between, say, swans and bears, how would we go about doing it? Does anyone want to make a guess? Give an answer. It's not a trick question. So hopefully you will agree with me that when we look at them, like we can think of several features like color, background, shape, and so on. And if we ask what does a neural network look at in order to like do the classification between these two things, there is strong evidence that neural networks only rely on like very few features. They don't really look at the image holistically, look at color, background, shape, or all these things, but look at only some features. So for example, in this paper by Gerhos et al., so what they show is that if you give the image of the skin of an elephant, then the model correctly classifies it as that of an elephant. But if it is given the image of this cat, and similarly, if it's given the image of this cat, it again correctly classifies it as a cat. But if there is an overlap between like the texture and shape, so you give a cat shape on elephant texture, then it turns out that it doesn't predict cat at all, and it still confidently predicts that it's that of an elephant. So the model relies more on texture as compared to shape. And similarly, in this other example by degrades et al., what they show is that if you when they tried doing COVID-19 positive versus negative classification using just X-ray images, it turned out that in the data set, training data set, there was a small marker on the top right-hand side of the negative images, which was maybe marked by the hospital staff or to indicate that this is actually a negative X-ray. And what the model learned is not really to understand the X-ray per se, but just looked at this marker and then started predicting it's negative. So whenever there is a test data point which actually is not marked like this, it's saying positive, even though the the X-ray could actually correspond to that of a COVID-19 positive sample, right? So the question we would like to ask is, why do neural networks learn only some features? And in particular, which features do neural networks learn among all the features that are available to it, right? So our main hypothesis here is that neural networks learn only the simplest features that are available for classification, even when there are more complex features that might still be useful for doing the classification. Okay, so let me give you a simple example using this picture on the right. So the blue data points are positive data points, and then the red data points are the negative data points. And each of the data point is in the two-dimensional space. So if you can, so as we can see, there are multiple different classifiers that we can draw to separate both of them. So one is the green classifier, which is a linear classifier which separates both of them. And then there is this orange classifier, which is not linear, but piecewise linear, which also can separate both of them. So how do we say which of these is better? So we can, one way to look at quantify the robustness of a classifier is using margin, which basically measures the closest distance of any data point to the decision boundary. So as you can see, the green one, green classifier has data points which are extremely close to the decision boundary. So the margin is basically 0, whereas the orange one is far from all of the both blue as well as orange data points. So the margin is strictly positive, right? So if you just compare in terms of margin, the orange classifier is more robust because it has higher margin, And if any data point has to change its prediction, then we have to add certain amount of at least some amount of noise for it to change its prediction. Whereas the green one is much less robust, because like a small perturbation around the boundary can easily flip over the points that are very close to the boundary, right? So in terms of robustness, we think that the yellow one is more robust, and this classifier is still not very complex, in the sense that from a representational power point of view, a one hidden layer neural network with ReLU activation can easily capture the orange color boundary. But however, when we train a model just using data from this kind of distribution, it turns out that it always learns the green classifier and never learns the orange classifier. So even though the models are capable of, representationally speaking, they're capable of learning a more robust classifier, they end up always learning the simple classifier because of simplicity bias. Okay? And this can be made more precise, particularly in the context of one hidden layer neural network under what is called independent features model. So we say that a distribution D satisfies the independent feature model if every sample xy from this data distribution, so x is the covariate and then y is the label. So x is the input and y is the output. Y is the desired label. The probability of x comma y can be decomposed as P of y, which is the probability of getting a label, and then product of P of xi given y, right? So different features are independent. So we can think of each of these xi as, say, color or background or shape and things like that. So, or size and things like that, where if I tell you that y is equal to a swan, then color and shape and size are probably independent. Similarly, for a bear, color, shape, size, and all these things could again be independent. So that's basically what the independent features model says. And the main theorem that we can prove about simplicity bias in one hidden layer neural network is that if D satisfies this independent features assumption, and it has at least one linearly separable coordinate. So in the previous slide, we saw that in the feature P1 direction, the data is linearly separable, right? So P1 is less than something for the positive and P1 is greater than something for the negative. So if you have at least one linearly separable coordinate, even if there are many other coordinates in which the data, the classes can be separated, but using a non-linear boundary, like a piecewise linear boundary that we saw earlier, then gradient descent using one hidden layer neural network, it only learns the linearly separable feature, meaning that the linear classifier that we saw in the previous slide, but it doesn't learn the more complex or piecewise linear, but at the same time more robust classifier, it will not be able to learn. Okay, so this can be shown rigorously in the independent features model setting. However, so all of these are still under some data assumptions, and if you want to understand to what extent is this true even for real data sets, the main challenge in going to completely real data sets is that we don't have a very clear notion of what a feature is and what is the simplicity of a feature, what is a feature, and how to measure complexity and so on. Okay, so that's why we designed this new data set that we call MSP data set, where we take we take an image from the MNIST data set, which is say binary MNIST, which is only 0 and 1, and then a binary CFAR, which is a cat versus dog kind of data set. The class 0 image of this new data set is obtained by concatenation of MNIST 0 and CFAR cat, and a class 1 image of this new data set is obtained by concatenating MNIST 1 and CFAR dog. Okay? So if you want to classify between these two classes, we can see either only the MNIST part or the CFAR part and still correctly be able to make the classification. Because if you see a 0 in the MNIST part, then we know that it's class 0. And if you see a 1 there, we know that it's class 1. Similarly, if we see a cat, we again know it's class 0. And if you see a dog, we know that it's class 1. However, when we want to understand, so if you look at what exactly is the model relying on, is it looking at the MNIST part or CFAR part, or is it looking at both of them? It turns out that the model is pretty much solely looking at the MNIST part. And this we can verify by doing what is called randomization test, where we randomize part of the image and see how the performance or output of the model changes. So if we randomize only the CFAR part, it turns out that in the top figure on the rightmost side, we see that the red is the output logics after CFAR randomization. They overlap with the blue logics, which are the original logics before, like on the original data set. So CFAR randomization doesn't have any effect on the model's output. Whereas the bottom one, where we are randomizing the MNIST part of the image, the red ones are completely different from the blue one, which says that the model is heavily relying on the MNIST part, but not on the CFAR part. Yeah. It is a question. This is also cross entropy. So I put informal. So there are many conditions there, which are there in a paper. So it's for cross entropy loss, for gradient descent, and one hidden layer neural networks in the infinite width limit. Yeah, yeah, yeah. So I'll come to, so that's a good point. So the margin-based loss function, so adversarial training can be thought of as one such. So it turns out that from an like global optima will be good, but from an optimization point of view, it's very difficult to properly optimize these margin-based loss functions.
Yeah, for any given data set, how do you check that equality is true? Like these distributions, are they known? How do you check whether a data set
so
is
I don't know if it is easy to check this condition, but the point of this is that this is a fairly natural condition when we think about how data is generated. So,
but the theorem starts with if it satisfies.
If it satisfies.
If it's an IFM.
So, I mean, eventually it doesn't matter if, I mean, so the way I see theory is not that theory is going to directly be useful in practice as such, but it gives us intuitions which can help us design methods. And then the efficacy of the method has to be developed on like real data sets. So even if we can design data sets like this, if I give you some images and so on, like there is no way that it will satisfy any condition like this. So I think of like these assumptions as creating a nice theoretical framework in which to think about and investigate this problem. But the real proof of the insight actually working will be how it works on actual real data sets. Okay. So hopefully I've convinced you that simplicity bias leads to learning of only the simplest features. And then because of that, we will not be learning all the features that are present in the data set. And the key point is that this can lead to brittleness both to distribution shifts as well as to adversarial examples. The brittleness to distribution shift happens when the simple features that are learned are not actually the true features which are consistent across different domains. For example, like if the simple feature was the marker in the COVID-19 setting, which was not the correct feature to look at when we went from like the train distribution to test distribution. So let me give you, so before I mention adversarial robustness, so let me give you a brief definition of what briefly introduce adversarial examples. So these are like very small, invisible to the eye perturbations that can drastically change the class of like model predictions of any given image. So for example, in the first image, we have like a dog image. And if we add a perturb noise, which is like 1/127, like very small of whatever is shown here, we get the rightmost image. Again, as you can see visually, we hardly find any difference, but the model completely makes a wrong prediction. And similarly in the second one. And the reason why simplicity bias leads to poor adversarial robustness is because, as we saw, simplicity bias can lead to smaller margin because it's not learning all the features, it's only learning the simplest features. And smaller margin basically means that the distance to destined boundary for many points need not be very large. So even small perturbations are enough to kind of flip over onto the other side of the destined boundary. Okay? And one of the approaches for improving adversarial robustness is what is called adversarial training, which is essentially similar to maximizing margin as was suggested earlier. So given data points x1, y1 to xn to yn, so the standard cross entropy objective or standard training objective will be either least squares loss in this case or cross entropy loss, so any of the loss functions, but applied on an average of yi and f theta of xi. So f theta of xi is my prediction on the given data point xi, and yi is my target. So what adversarial training does is that instead of xi, we take a maximum over all possible xpidal I, which are in an epsilon ball around the given point, so that the predictor function is actually smooth in an epsilon neighborhood around the given point xi, yi. Okay? So the table on the bottom, what it shows is that even though adversarial training attempts to fix simplicity bias by maximizing margin, in practice, it does face optimization difficulties. And eventually, even L infinity adversarial training doesn't improve the CFAR randomization accuracies on the MSP data set, and so consequently doesn't check simplicity bias. So another standard approach for improving robustness is what is called doing ensemble learning, where we train multiple models using some kind of differentiation for all of them by either selecting different subset of data, or we can do different random initializations and so on. So the main hope is that each of these models learns to depend on different features, and so they will. So when we put them together, they'll be more robust, and together they'll be able to learn all the different features collectively. However, what it turns out is that when we have features of similar complexity, ensembles work well. So on this example on the in the middle, like MS5, where we see that the x coordinate is one feature, y coordinate is another feature. So we can, and green or yellow is one class, and then the cyan color is another class. So we can draw a we can do the classification based on either only the x coordinate or only based on the y coordinate. And the number of pieces in the piecewise linear classifier that we need is exactly the same in both of them. So when we train independent models, different models end up picking different, like some pick x coordinate, some pick y coordinate, and so on. So consequently, in the rightmost plot, when we look at the red graph, where the x-axis is indicates the ensemble size and the y-axis is the accuracy. As we increase the number of models in the ensemble size, the accuracy of the model increases because different models end up learning different features. However, in the left-hand plot, where we have this L hat MS7, where in the x-axis it's linearly separable, almost linearly separable, but in the y-axis it's not linearly separable. It's separable only by a piecewise linear classifier. It turns out that even when we train multiple models, all of them end up relying on the linear classifier, and consequently, when we put them together in the ensemble, their robustness does not increase, as is indicated by the blue line in the rightmost figure, which shows the accuracy plot. Okay? So hopefully, I've convinced you that simplicity bias is an important issue which can lead to brittleness, both to distribution shifts and adversarial examples of these neural networks. And existing methods like adversarial training as well as distillation don't automatically fix simplicity bias. So if you want to fix simplicity bias, you want to come up with new algorithmic insights. And in particular, before we come up with new algorithmic insights, it seems that we need to understand more in more detail how simplicity bias manifests more precisely, so that we can use those in the through algorithmic insights to actually mitigate simplicity bias. Okay? So in order to understand like the more precise manifestation, we take this test-bed data set, which is called colored MNIST, and the task is to classify mostly red zeros versus yellow ones. So while there is high correlation between the color and digit, the label is primarily is only dependent on the digit. So there could also be some yellow zeros and red ones. So only the digit is the correct, is giving us the correct label, but color is still very highly correlated with the label. So it acts as a spurious feature. And you want to see in what way does color play a role in terms of like the prediction of the model. Okay? So the first key insight that we develop in this line of work is that there is feature replication in the penultimate layer corresponding to simple features. So what I mean by that is that if we take a 3-layer CNN with 32 penultimate features, penultimate hidden units in the like in the penultimate layer. So in this figure here, so the rightmost thing is the output logic, and then the one just before that are the penultimate layers. We see that most of them are actually correlated with color as opposed to shape. So in the table here, what we see is that out of the 32 penultimate layer features, we see that 26 of them have much higher correlation with color as compared to the shape, whereas only 4 features have much higher correlation with shape as compared to color. And there are 2 more neurons which don't have very high correlation with either color or shape. So out of the 32, only 30 have very high correlation, and among them 26 have much higher correlation with color as compared to shape. Because the final layer primarily depends on the penultimate layer features in order to do the final linear classification, it turns out that the output correlation with color turns out to be much higher compared to that with shape. Okay, so what we can, so let me try to illustrate this through a simple example as well. So if we have these yellow and blue data points of different classes, if we train a linear in this 2-dimensional data set, if we train a linear classifier, so the max margin classifier is one that goes exactly between them and maximizes the distance between of all data points to the decision boundary. Whereas if you have feature replication, meaning that the y coordinate is replicated 5 different times, so we are now in a 6-dimensional space and we are doing linear classification in six-dimensional space, where the second to sixth coordinates are nothing but a replication of the y coordinates here. And we train a linear classifier in that space and then project it back onto the original space. We see that the classifier is more reliant on the y coordinate as compared to the x coordinate, right? So what it means is that the more and more a particular feature is replicated, the classifier is going to rely more and more on it. And because the simple features are replicated more in the penultimate layer, the overall predictor is going to depend more on this replicated feature as opposed to the other non-replicated feature. So the way we fix that is using the feature reconstruction regularizer, where we add an additional loss term. So LSTD is the standard cross entropy loss. In addition to that, we add this LFRR, which is the feature reconstruction regularizer loss term. What it does is that it takes the purple nodes, which are the output logic, and then it tries to reconstruct back the previous green nodes, which are the penultimate layer features, and it reconstructs them as this red ones. And then we want the red ones to match the green ones. So what it means is that the final logic should not lose any information that was present in the penultimate layer. And even if there is replication, because if there is statistical independence between the replicated features and the other features, then the red ones should be able to replicate, should be able to reconstruct all of these previous ones. And this enables the purple, like the logics in the purple layer to be more dependent, not only on the replicated features, but also on the non-replicated features. So more concretely, so we take the same example that I was showing earlier, and we look at the phi representation. But if we add this FRR loss sum and then train the linear classifier along with that, we see that we again recover the max margin classifier, even when there is feature replication. And because of this, even when there is shift in the y coordinate, the model is more robust because of the because it is not aligned with the y coordinate. It's not relying more on the y coordinate, but rather relying both on the x coordinate and y coordinate to make it prediction. Okay. So that was the first one was feature replication. The second key insight is that these replicated features are also often non-robust. In the context of the color in this model, what it means is that if we train two models, one where color is randomized and the model has to rely on shape in order to do the prediction, and the other one where shape is randomized and the model has to rely on color to do its prediction, it turns out that the test accuracy for both the models is close to 100%. However, when we look at the adversarial accuracy with a perturbation of 0.1 in both the cases, the model that depends on shape is much more robust compared to the model that depends on color. So in the table on the bottom right, we see that the model that depends on shape has 85% adversarial robustness compared to the model that depends on color, which has only 53% robustness. So we want to encourage the model to rely more on the robust features as opposed to the non-robust features. And one standard way to do that would be to use adversarial training, but it turns out that adversarial training leads to a loss in standard accuracy. And as we saw earlier, standard accuracy is closely, like highly indicative of the accuracy that we are going to get in the out-of-domain setting. So we don't want to use complete adversarial training because it affects the standard accuracy negatively. So what we can do here is something called adversarial fine-tuning, which is a sweet spot between standard training and adversarial training, where we first train the model using standard training and we freeze the entire backbone until the green part. And then we only do adversarial fine-tuning on the final linear layer, because the penultimate layer, even though there is feature replication, pretty much all the features are still represented. And the final linear layer is now encouraged more to depend on the robust features as opposed to non-robust features. And this lets us get the benefit of adversarial robustness without having to suffer from drop in standard accuracy. Okay. Yeah.
Uniform replication of all the features, or it depends on the, as you said, in the penultimate layer, how they are appearing, like the correlation, most of the features are highly correlated with color and only few features were correlated with shape. So would you like to create more replication of the shape-based features or something like that?
So that's also
like
a good direction. So we haven't explored that. What we are here trying to say is that given that there is replication in the penultimate layer, you want to design the final layer training so that it's robust to that replication. So even when there is replication, it still achieves max margin classifier in more like an information theoretic sense. Yeah. Okay. Okay. So the final component that we have been able to that we did in this line of work is that distillation is a well-known approach to improve the accuracy of small models by beyond the standard training. However, in the context of out of distribution robustness, it turns out that vanilla distillation doesn't work. So let me first explain what distillation is, and then explain why we have to do something differently in the current context. Okay. So distillation, the main idea behind distillation is that if we first train a large model, which is theta hat big, which is trained on like ground truth data xi and yi, and then we use its predictions f theta big of xi as a target for the small model. This small model performs better compared to training the small model directly on xi yi, which is the original ground truth data, right? And the point that we want to make here is that we want to understand whether we can directly use distillation to also improve out of distribution robustness, just like how it has been shown to improve standard robustness, standard accuracy. And it turns out that by itself it doesn't work. And the main reason is that the distillation works because the incorrect logic, meaning that the logic corresponding not only to the ground truth label but also to the other labels of the big model are actually informative in teaching the small model on giving more information to the small model. Whereas when we do adversarial fine tuning and FRR in the previous, as I mentioned earlier, it turns out that the teacher's logic in the incorrect options are not very meaningful and more noisy. So in order to overcome that, we add a regularization term which ensures that even the incorrect logics of the teacher model are meaningful. And consequently, if we train the teacher model using both distillation, using both literal fine tuning as well as this regularization term, which encourages the incorrect logics to be smoother, it turns out that this leads to better teachers. And once we use this feature, we can then, once we train this feature, we can then use it to distill into a smaller student model. And the overall approach is what we call DAF, which is distilling adversarial fine-tuned model. So we evaluated both DAF as well as FRR on domain bed, which is one of the most common benchmarks for testing out of distribution robustness. So this is a benchmark, meaning that it's a collection of multiple different data sets, including facts and some of the initial data sets that I showed you on the first slide for out of distribution robustness. So for example, the data sets look like this. So facts is a collection of photo, art, cartoon, and sketch. So during training, we might get data points only from sketch, cartoon, and art. And then at test time, we want to be able to do well even on photos, right? And on this benchmark, we achieve a state-of-the-art accuracy number. So in particular, like ERM achieves an accuracy of 63.3 on domain bed. And after several years of work, SWOT, which was the previous state-of-the-art, achieves about 66.8% accuracy. Both DAFT and FRR individually can improve over SWOT. And when we combine both FRR and DAFT, like it provides substantial improvement of 1.6 percentage points over the previous state of the art. And this is again like somewhat complementary to SWOT, which does some kind of weight averaging, right? And this can again be combined with SWOT to improve these numbers. But as we can also see, like these numbers are still far away from like 90s and so on. So there is still a significant scope for improvement in improving the out of distribution robustness of these models even further by using new insights. So just to conclude, so hopefully I've convinced you that neural networks suffer from extreme simplicity bias and that this is a key reason for the brittleness of neural networks to distribution chips. And in this line of work, we have identified like two particular ways in which simplicity bias manifests itself. So one is feature replication, the other one is non-robust features. And based on these insights, we again like design two different methods which can fix both of these issues and achieve state-of-the-art result on the domain bed benchmark. Looking at future directions of work, in addition to our work, there also have been quite a few other works which try to mitigate simplicity bias by training diverse networks and so on. So coming up with a unified framework for mitigating simplicity bias, which kind of encapsulates all these different ideas that people have come up with, it should be an interesting, very interesting line of work. And I would hope that something like this can actually make a substantial improvement, further improvement on out of distribution robustness on some of these benchmark data sets. And as we are also all aware of, so currently it's there of large foundation models, including like particularly large language models. And we know that there's still several issues, but the investigation of simplicity bias in the context of large language models is still mostly unexplored. So it'll be very interesting to see if the fact that these models are trained on extremely large and diverse amounts of data automatically mitigates simplicity bias, or if there is still simplicity bias in these models, are there any ideas that we can use to kind of mitigate simplicity bias and improve the robustness of these large foundation models. So these are some interesting directions. And finally, one way to use simplicity bias is also to perhaps use it for doing interpretability, using interpretability methods to identify what are the simplicity bias that the model suffers from, and then using it to do a more thorough collection of data sets and more diverse data sets, which can then further mitigate simplicity bias. So